Welcome back everyone. In this video we will talk about regression or polynomial regression. So we have two types of regression. One is linear, another is non-linear. So in this video we will talk about linear regression. Now what do I mean by linear regression? Let us say I have a data set x, y. That is, if I plot that data set on this xy graph, then I have value of y corresponding to each value of x. So this is my data set having random values. Now out of this data set, I want to find out a function that best represents this data set or the nearest representation of this data set. Ideally, the best representation of this data set would be that this function is satisfied for each value of x and y. But that cannot be the case because these points are not having any functional form, so we cannot write that. We want to give a approximate representation of this data set. Now in polynomial regression that has the Taylor series form, we suppose I have this y and that is a0 plus a1x plus a2x square, so on and so forth. Now this is called linear polynomial regression. That means this y is the best representation of this data set. Now why this is called linear regression is because y is linear in parameter a. Now if y would have been non-linear in parameter a, then we would have called it non-linear regression, such as y is equal to a0 plus a1 to the power of x plus a2 4x square plus so on and so forth. Now here this y is not linear in this parameter a, so this will be non-linear. Now since we are only talking about linear regression in this video, we will talk about this functional form. So I have this data that is x and y, which is x1 y1, x2 y2, x3 y3 and xn yn. So this is my data set. Now with linear regression, I want to represent this data set as y is equal to a0 plus a1x plus a2x square plus so on and so forth. Now if I terminate this series, this Taylor series, why we are calling this as a Taylor series is because this a1 is zeroth order derivative, this a0 is zeroth order derivative, this a1 is first order derivative, this a2 is linked with second order derivative, that is second order derivative divided by factorial 2. Now suppose if I want to terminate this series up to this 3 points only, y is equal to a0 plus a1x plus a2x square. Now ideally speaking, if this is the perfect representation of this data set, these x and y should satisfy this function. But since we are calling this is an approximated representation of this function, then we will try to somehow fit this data in this functional form. So in that case, each of these points should satisfy this function. So I have this y1 is equal to a0 plus a1x plus a2 x1 square, y2 is equal to a0 plus a1 x2 plus a2 x2 square, yn is equal to a0 plus a1 xn plus a2 xn square. Now this is my matrix system, that is matrix P, which is 1 x1 x1 square, 1 x2 x2 square, 1 xn xn square, and then vector a0 a1 a2, if we call it a is equal to y1 y2 and yn. So I have this matrix system here, that is PA is equal to y. Now if I can find out the solution of this matrix system, I know the parameters a0, a1 and a2, and that means I have this functional form. Now the task remains that I want to find out this PA is equal to y, or let's say PA is equal to y, where P is 1 x1 x1 square, 1 x2 square, 1 xn square, a0 a1 and a2 is equal to y1 y2 yn. Now remember, this is not a square matrix. This is having n rows and 3 columns only. So this is of n cross 3 matrix, this is of 3 cross 1 matrix, and this is of n cross 1 matrix. Now we cannot directly invert this matrix system. So suppose, since everyone is known to this form, so I am calling this matrix A, I am calling this as vector X, and I am calling this as B. But the problem with this matrix system is that A is not a square matrix, so we cannot directly invert it. We will have to convert this matrix in such a way that we get this as a square matrix. So I have this AX is equal to B. Now multiply both sides with A transport. Now if I do that, A transport X is equal to A transport B. Now this matrix becomes n square matrix. So I have this A transport A times X is equal to A transport B. Then I can find out X, which is vector A0, A1, A2 as A transport A inverse times A transport B. And this is easily solvable system. So here we will find out the inverse of this matrix, then we will multiply it with A inverse B. Now if I find out the A0, A1 and A2, I have this function y is equal to A0 plus A1x plus A2x square. So this is called linear regression. How we will find the linear regression is, first we will find the matrix A, that is 1 x 1 x2 square, 1 xn square. Then we will find the matrix B, that is y1 y2 and yn. Then we will find out the A transport A and A transport B. We will multiply these two, A transport A inverse multiplied with A transport B, and that will be my solution vector A, and A is nothing but A0, A1 and A2. So this is how we can do the linear regression with the help of Taylor series. So these are basically very simplified, very simple application of Taylor series. In the next video we will talk about nonlinear regression. Okay, thank you so much.